So welcome back to part 3 where we're talking about the Jordan basis. So I left off with this kind of big matrix here. Now let me just zoom back in so we can see things a little bit better. And now we're ready to define what a Jordan basis is. So a basis for a vector space is called a Jordan basis if with respect to this basis you can write your matrix associated to it as a bunch of block matrices. Okay, so we have a bunch of block matrices, and with the additional property that each of these blocks looks like lambda I up to lambda I down the diagonal, and then you have ones on the diagonal directly above, and then zeros everywhere else. Okay, so this is exactly kind of what we're seeing over here because we have kind of zeros and then ones above the diagonal. Okay, so maybe I'll make this a little clearer that these ones go all the way down. Okay. Okay. So as a corollary of what we just proved, right? Or we haven't proved it, but a corollary of the statement is that if you have a nilpotent operator, then V has a Jordan basis, right? And the proof just comes from the matrix above. See the matrix above. It has the correct form. Okay, right? So I'm talking about this particular matrix right here. Okay, so if you assume the result about nilpotent operators, we come to kind of like one of the big results in linear algebra, and definitely one of the main results of chapter 8, which is that if you have a complex vector space, then every operator has a Jordan basis. So you can find a basis that has it, that it puts the matrix into that shape. And why is that? Well, let's say you know what the eigenvalues are. And so we've used this result a number of times that you can decompose your vector space into a bunch of direct sums of generalized eigenspaces. Now for each t minus lambda I times the identity operator restricted to one of these eigenspaces, we know it's nilpotent on that particular subspace. So it's nilpotent on this subspace. So we can find a basis. We can find a Jordan basis. Oops. Oh, you're already in red. We can find a Jordan basis of G lambda T, right? And then all you're doing, so we can find a Jordan basis for this part, we can find a Jordan basis for the next part, we can find a Jordan basis for the next part, and what you're just doing is you just put all the bases together. Put all the bases together, and this becomes a basis for V that puts MT into Jordan form. Okay, so that's basically it. So the real hard work is actually proving the result of the nilpotent operator. Okay, and let me just kind of give you an example of this. Okay, we won't go into all the details, but I will want to say something about that in a second. So in lecture 23, we looked at this particular linear operator. We were looking at a linear operator from C4 that took x1, x2, x3, x4 to this new 4 tuple. And we showed that if you use the basis, and I have room here, 1, 0, 0, 0. The next vector was minus 1, minus 1, minus 1. The next basis is 1, 0, 1, 0. And the next basis element was 0.3 minus 1, 0, 0. So we kind of worked out all the details to show that if you use this basis, then you got the associated matrix was a form of bunch of blocks, a block diagonal matrix, but then we ended up with kind of this junk up in the top side. But if instead, if we had used a different basis, and the basis that we would use would be 1, 0, 0, 0, 1, 1, 1 minus 1, and then we use 1/5, 0, 1/5, and 0. And if we use 17/300, 1/30th, 2/30th, and 0 as our basis, if we use that, then the associated matrix that you get is going to be 10, 0, 0, 0, 0, 20, 0, 0, 0, 1, 20, 0, and 0, 0, 1, 20. Okay, and this is clearly the Jordan form. Right, so we can see the two blocks, and they have the property that we allow some ones on the upper diagonal, but then zeros everywhere else. Okay, now it may look like I just pulled this out of the air, but it's actually really hard to kind of, well, not hard, but it's kind of a complicated way of doing this. So I've made an extra video kind of lecture 25 extra, that's what you should look for, where I work out the details. I work out the details for this example. Okay, so this course is really more about theory, so I'm not actually going to expect you to be able to kind of crank out some of the, be able to actually find these things necessarily, but it would be good if you watch it and maybe try some examples on your own. Other courses, I think 3AFO3, if you take that course, they really kind of want you to know the Jordan form and be able to find it. Now, you'll see kind of when I work out the video that it basically takes me to 30 minutes, 30, 40 minutes to work out all the details of why this is the correct basis. Okay, so we're going to pause here, and then when we come back, I won't explain the proof in all detail, but I will explain the main steps of why this proof works. Okay, so I'll see you in the last part of today's lecture.